All right, so we're going to start by taking the grams of oxygen, so this reactant, and figuring out how many grams of product it would produce. So there's several steps in getting here. So when you're going from grams of one element or compound to grams of a different element or compound, you need to get it in moles first, because the coefficients in front of each element or compound, those represent the number of moles. So I can't use this balanced chemical reaction unless I'm in moles first. So whenever you have grams, your first step's always going to be to get moles so that you can use the balanced chemical reaction. So my process would be starting in grams of oxygen. I just said I need to get into moles first. Once I'm in moles of oxygen, now I can compare it to a different element or compound. And I can do that using the coefficients in front of those two. So the two that I'm comparing is oxygen to product. So I'm going to go from moles of oxygen to moles of product. And this step, going from moles of one element or compound to moles of a different, this is that mole ratio step, where we're using the coefficients in front of those two elements or compounds to get between the two. Now, once I'm in moles of aluminum oxide, I'm not stopping there because the question asked me how many grams of product. So I'm going to keep going from moles, then to grams. So what do I need for each of these steps? Well, we said mole ratio to go from moles of one element or compound to moles of a different. But for these two steps, what do we need? So we're going between grams and moles. So to go between grams and moles, we need that Mn, the molar mass. So over here, it's grams and moles again. So we need molar mass again for this step. Once we know the information we need, let's gather that information before we start doing our calculation, before we start our railroad tracks. So I'm going to start with this first step, and it says molar mass, but molar mass of what? So when you're figuring out molar mass of what, it's of whatever element or compound that you're trying to convert between. So I'm trying to go from grams of oxygen to moles of oxygen. So I need the molar mass of oxygen. So that I'm going to have to calculate. So I look at how many atoms of oxygen I have, which are 2. I multiply that by the molar mass of oxygen on the periodic table. So I find oxygen on the periodic table, and it tells me the molar mass is 16.00. So my total molar mass is 32 grams per mole. And remember, this is a conversion factor. That per sign can be an equal sign. And you can write it 32 grams is equal to 1 mole. So this is the conversion factor to use for that first step. So I'll write a 1 by it for step 1. Now for the second step, right here, once we're in moles of oxygen, we want to get to moles of aluminum oxide. We need the mole ratio. To figure that out, find the two elements or compounds that you're comparing and look at their coefficients. So I have oxygen and aluminum oxide, so a 3 to 2. So this means 3 moles of oxygen is going to produce or equal 2 moles of product. So that's my second conversion factor. 3 moles O2 is going to equal or make 2 moles AO2O3. So that's my second step, my second conversion factor. I need one more. So step 3, it's going to be molar mass again, but this time it's not oxygen we're going between, it's aluminum oxide. So I need the molar mass of that guy. I'm going to do that over here to the side to give myself some room. So molar mass of Al2O3. Make a list of all elements present. We have aluminum and we have oxygen. The number of atoms of each are the subscripts. So 2 aluminums, 3 oxygens. Looking up on the periodic table their molar masses. I know oxygen's 16. I don't know aluminum off the top of my head. 20. It says 26.98 on this periodic table. Depending upon the periodic table you're looking at, they sometimes round and sometimes don't. This one in the classroom does not, so 26.98. So multiply across and add them all together. So I get for the total molar mass 101.96 grams per mole. Remember, that per, that slash, can be an equal sign. So 101.96 grams equal to, instead of the slash, and then it's just 1 mole. So this is going to be the third conversion factor. I'm going to write it over here to keep them all together. Now I'm going to go ahead and start my railroad tracks. I know I'm going to need this much room. Let's erase this. All right. So starting with the 9.5 grams, right? The number given in the initial question. 9.50 grams of O2. My first step, I'm using the molar mass of O2 to go between grams and moles. So here's my molar mass. I want to take and put the 32 grams in the denominator on the bottom, because I want my grams of O2 and grams of O2 to cancel. So now, if I do this division, 9.5 divided by 32, I'm here. I'm at moles of O2. So my next step is to use the mole ratio so that I can get into moles of product. I'm trying to see how much product I'm going to form if I use all of that oxygen. So the mole ratio is given here. And we're going to put the moles of O2 in the denominator to cancel it out. So we have 3 moles O2. Just going to put the other part of that conversion factor, the 2 moles of aluminum oxide, on the top. That way, moles of O2 cancel. Now I have moles of aluminum oxide, so I'm close. I know how many moles of product I'm going to form. Now I'll use the molar mass of that product to figure out how many grams of product I'm going to form. So my last conversion factor is the 101.96 grams, and grams is what I want, so I'm going to put that on top. And that's grams of aluminum oxide. That's how much 1 mole with aluminum oxide weighs. So cancels out my moles, so I'm no longer in moles of product. Now I have grams of product. So calculate this out. Multiply everything on top. So 9.50 times 2 times 101.96, and divide that whole thing by 32, whatever's on the bottom, times 3 times 1. I get 20. Looks like quite a lot. Isn't that right? Let's hope so. So I get 20. How many sig figs? There were 3 in this number, so we want 3 in the answer. 20.2 grams of product. All right. So I'm going to write this. I'm going to write O2 will produce 20.2 grams of product. The reason I'm writing this off to the side is because we're using each of these reactants separately. We're saying if I used all my oxygen, how much product would I make? What we do next is if I use all my aluminum, how much product would I make? And then once we have the amount of product made by each, Whichever one makes the least is the limiting. So we need to keep track of this number. So we erase this, and we're going to do the same thing, but using the aluminum given, the 7.2 grams of aluminum. All right, so this time, color, 7.2 grams of aluminum, and we're going to see how many grams of product that's going to make. All right, so same steps. I'm in grams of aluminum. I need to get to grams of aluminum oxide. I can't compare grams of two different atoms or molecules. I need it in moles first. So that's the first step, is to get my grams into moles so that I can compare them using that balanced chemical equation. So grams of aluminum is where I start. My first step is to get those grams of aluminum into moles of aluminum. Once I have moles, well, the coefficients represent the moles. So I can compare now between the reactant and the product using a mole ratio. And then the last step, because it's asking for how many grams of product, is to get our moles of products into grams of product. All right, so let's write down all the information we need for each of the steps. So step 1, going between grams and moles. Anytime you go between grams and moles, it's molar mass that you need to get there. More specifically, molar mass of aluminum in this case, because that's the reactant we're looking at. That one's easy because you don't have to calculate it. So it's 26.98 grams of aluminum is equal to 1 mole of aluminum. So I just looked that up on the periodic table, no calculation needed. For the next step, the mole ratio, step 2, now we're looking at the coefficients between aluminum and aluminum oxide. So these two guys. So in this case, it's a 4:2. So step 2 says that 4 moles, because that's what the coefficient stands for, is moles, of aluminum is going to produce equal to 2 moles of aluminum oxide. So this will get me to my moles of aluminum oxide. Third and final step. Notice we're going between grams and moles again, so we're going to need molar mass. I know I erased the molar mass of that guy, but we already calculated it. What was it? 101.96, I believe. 101.96. Looking at the eraser mark so I can not calculate it again. And that was grams of aluminum oxide equal to 1 mole. All right. 3 conversion factors ready. Start your railroad tracks, and we're starting with our grams of aluminum, 7.2. 7.2 grams of aluminum. Now, first step, molar mass. We're going to use the molar mass of aluminum to get to moles of aluminum. Remember, you're trying to cancel out grams of aluminum, so you want the moles on top and the grams on the bottom so that they're on opposite sides of the horizontal line and they will cancel out. Now we're at moles of aluminum. So we're going to use our mole ratio next, that 4:2 ratio, to get to moles of product. So I'm going to put the moles of product on the top because that's what we're looking to get, L2O3, and the 4 moles of aluminum on the bottom so that those cancel. Now, last step. we're at moles of aluminum oxide. We want to get to grams. So we're using the molar mass. We get 101.96. And then moles on bottom. Multiply across, divide by what's on the bottom. So by multiplying across, I'm taking 7.2 times 2 times 101.96, dividing that by everything on the bottom, so 26.98 times 4 times 1, I get 13.6. And that's grams of product. So what this just told me was that if I used all of my aluminum, all 7.2 grams, it would produce 13.6 grams of aluminum oxide. So what that means is, once the aluminum is gone, I'll have 13.6 grams of product. I'm going to have extra or excess oxygen. I'm never going to get to 20 because I don't have enough aluminum to get me there. So since I don't have enough aluminum to get me there, since aluminum makes the smaller amount of product, aluminum is going to be the limiting reactant. So whichever two of the reactants makes the least product, that's the limiting. So when it's asking how many grams of product would form, well, the limiting reactant, the limiting reagent, is the one that determines how many grams of product, and in this case, it's 13.6 grams. All right. So, to bring in the last topic, this 13.6 grams that we just figured out, that's how many grams of product would form due to the limiting reactant to aluminum. Since aluminum is going to be the first reactant used up in the reaction is going to stop once that 13.6 grams is made. This 13.6 grams, this is called our theoretical amount. And we actually talked about the word theoretical before when we did percent error calculations in class as well as percent error calculations in lab. So what theoretical means is that is the maximum amount of product I'm going to make. If I did everything perfectly during this experiment and didn't spill anything, didn't lose any residue inside of any of my flasks or anything like that, I would get 13.6 grams. Okay, but we know in the lab, we never get 100% yield. We never get 100% of what we're hoping to get because there is human error. We do spill a little bit here and there, or we don't get every last little drop out of every flask. So there's a calculation to do that we haven't talked about yet that helps us figure out what our percent yield is. So far in this class, we have talked about percent error only. So let's look at that equation quickly. For percent error, we've used the actual, I should say experimental minus the theoretical divided by the theoretical times 100. So the percent error equation we've used before. The theoretical being the actual value, the true value, the value you get from a table. Well, theoretical can also be the maximum amount, the amount that you should get out if everything went perfect. And we're comparing it to the experimental using this equation, and the experimental being, well, what did we get when we actually did this experiment? So the percent error tells us what percent of mistakes we've made. So we always wanted percent error to be really low, because a low percent error means very little mistakes. Well, another equation we use to test our ability in the lab is percent yield. And for percent yield, it's a very similar equation because we're taking the experimental and dividing it by the theoretical and multiplying it by 100. So we're skipping out this last part where we subtract the theoretical from it. So for percent yield, we're looking at how much of the possible did we make. What that means is high percent yield equals little mistakes. Because if you made 100% yield, the highest you could get, that means you made absolutely no mistakes. You got all of the product you could have possibly gotten from that experiment. So let's look at a problem using the percent yield equation. So I'll leave that percent yield equation up. And we'll say we did this experiment. We added solid aluminum, gaseous oxygen, let the reaction go, and we gathered, isolated how much product we made. And say what actually came out, the experimental, was 11.9 grams. Say that's how much, once I isolated the product and massed it on the scale, I saw 11.9 grams. That's how much I made. So I'm going to compare this 11.9 grams, my experimental value, to the theoretical amount that we just figured out. And to do that, it's plugging them into the equation. So we just said the experimental, once I did this experiment, I got 11.9 grams. I'm going to divide that by what I could have gotten, 13.6. Then I'm going to multiply it by 100. So the reason I left the units in here is so you could see that the units cancel. I've had a lot of people putting gram percent when they're doing percent error calculations, and so I don't want that to happen for percent yield as well. The grams cancel, the only units on it are percent. So doing this calculation, 11.9 divided by 13.6, and then times 100, I get 87.5. Do I need 3 sig figs? Yes, I do. So 87.5%. If I got 100%, that means I made everything with no mistakes. So this is good. It's a high percent yield. Higher percent yield means little mistakes. Well, I want to use these same values to do percent error so you can see the difference between them because we've been using percent error already. Might help you understand a little bit better why we use one versus the other. So for percent error, it was experimental, 11.9, minus the theoretical, being that 13.6, and then dividing it by the theoretical, and then multiplying by 100. Now remember, this has absolute value bars on it, because when I do this subtraction, it is going to be negative. But because of the absolute value signs, I just change that negative to a positive. Divided by 13. And I get 12.5%. So smaller number, because for percent error, the smaller the better. It means little mistakes if it's small. But also notice something else. What happens if I add these two? When I add them together, it equals 100%. Because this is, how much did I make? I made 87% of what I possibly could have, meaning that I had 12% worth of mistakes. If you have extra time on the exam and you want to check, your work for your percent yield, you can also do percent error and make sure that they equal 100 together. All right, so that's all the topics for this next exam, which is a week from today. On the next video, I will be starting the review. You will have there'll be 2 review videos posted, one this week and one on Monday of next week. The exam does open Sunday if you want to take it early. If you do the practice exam and the practice quiz I have and you're doing great on them, I'd go ahead and take it. But if you want that extra review video, that won't be out until Monday. But I will do one this week as well, so there will be 2 available. Let me know if you have any questions that you want me to do and post. Otherwise, I have a review sheet that I'm just going to start doing problems with if there are no questions.